All right, let's talk about wind for a second. So wind is the horizontal movement of air due to changes in pressure. So because of pressure changes, our air is going to move from one place to the other. So rapid changes are going to cause stronger winds. So the bigger the pressure difference is between two areas, the faster my wind is going to move. And we can see that on this map that's showing different pressures, right? This is an isoline map. These are showing isobars because this is barometric pressure. On this isobar map, we can see where the wind is going to be blowing the fastest or moving the fastest. And it's going to be where these lines are closest together because that's going to represent the biggest change in pressure over a geographic area. So the closer those lines are together, the faster the wind we can expect to encounter in that area. So right here, over here by the East Coast is where we're going to be seeing the fastest winds in this area because they are much closer than all the way over here on the West Coast. So as I was saying, you can see that our lines are the closest here on the East Coast, and I've highlighted that right there for you. That's where we're going to see the strongest winds, the fastest winds. So, instrument used to measure wind is called an anemometer. It determines wind speed. A wind vane, or a weather vane, determines wind direction. So those are two different things. We measure one with an anemometer, that's our speed, and our wind vane is going to measure our direction. Winds are named for the direction from which it comes, not the direction that it's going. So a north wind is going to be coming from the north and going to the south. So if I look at these winds, I want you to take a second, pause the video. So I want you to take a second and I want you to name these winds based on what direction they are coming from. So I'll give you a minute. All right, so here are our wind names based on the direction that they're coming from. How'd you do? All right, there's two types of winds that we're going to encounter. First, that was the local winds, right? The wind blowing around every single day in small areas. There's another type of wind, that is global wind. So these are winds that are driving and moving storm systems and pressure systems all around the Earth. So these are naturally occurring winds in the atmosphere due to major pressure changes, latitude and angle of insolation, right? Those are going to be the things that are going to affect these winds the most. Where they are positioned in their latitude and what the angle of insolation or how much sunlight they're receiving are. So we can take a look at this chart. It's on page 14. So winds always blow from high pressure to low pressure. So they're always going to go from areas of higher pressure to low pressure. So low pressure is going to be wet. Remember what we said, as we add those water molecules into our air, we are lowering the pressure. And high pressure is going to be dry. So wind is always going to move from dry areas to wet areas, from high pressure to low pressure. All right, this chart is located on page 14 of your reference table, and it shows us all of the major wind belts that are on Earth. And you can see the wet wind belts right here, like I've got one right here at the equator at 0 degrees latitude, are going to be rising. Notice how these arrows right here are rising up from the surface of the Earth. The dry areas, we've got one here at 30 degrees north and one at 30 degrees south, are going to be sinking. So our arrows are going to be going down. These are high pressure areas. And you can see they kind of alternate as we go north and south of the equator. We've got a wet area right here at the equator, then dry at 30, then wet at 60, and then dry again here at the pole at 90. And the same thing happens on the southern hemisphere, right? We've got wet at 0, then dry at 30 degrees south, then wet at 60 degrees south, and then dry again at 90 degrees south. And that all has to do with the fact that the angle of insolation is changing as we move over the surface of the Earth. So weather systems generally follow these planetary wind belts. In the US, they move from the southwest to the northeast. So typically our weather is going to be moving from here in the southwest, Arizona, Southern California, Nevada, Utah, all the way up to here where we are in New York State. So these planetary winds are going to move major storm systems like hurricanes. Hurricanes form off the coast of Africa right here. and they move westward across the Atlantic Ocean towards the United States. Why is that? Well, they are going to be following these planetary belts of winds that are moving west towards the equator. They're going to be going the opposite direction a little bit further north. That's why that and the Coriolis effect are why our storms are going to start turning back out towards the Atlantic Ocean. So let's talk about local winds. So local winds are air movement due to small scale convection cells, right? They're not these huge planetary winds that we were talking about earlier. So convection, air is going to warm and rise and then cool and sink, causes changes in the air pressure at the surface. All right, so the next thing we got to do is figure out why are we getting these local winds? Why are we getting these big differences in pressure? Now, for our planetary winds, the reason for that is because of latitude, right? The closer something is to the equator, the more direct those sun's rays are going to be, and the faster they're going to heat up the air, and the more it's going to heat up the air. The closer we get to the poles, the less that angle is going to be, and you're going to end up with cooler temperatures and cooler air. But the reason why we're getting these local winds has to do with the material that those rays of sunlight are hitting, the material that they're warming up. The Earth isn't made of the same thing, right? Most of our surface is covered in water, and some of it is land, right? Those two things are going to heat up and cool down differently. Now, we describe this as what I got up here as specific heat. So this is the amount of energy it takes to heat up a gram of a substance 1 degrees Celsius. The higher the number, the more energy it takes. So for example, copper, which is in your reference table, is 0.38 joules per gram times degrees Celsius. Now that's going to be our specific heat. Now if I look at water, it's 4.18. Water is going to heat up much slower than that copper, right? And you've seen this, like if you heat up a steel pan on the stove, it heats up much faster than the water inside of it, right? The outside of the pan is going to be hot a lot faster than the water that you're trying to boil inside of it. So, question being, does it take longer for the land or water to heat up? So water, the specific heat is higher, and it means that Lake Ontario is going to stay warm into the fall but remains very cold in the early spring. So the flip side of this, if something heats up quickly, it's also going to cool down quickly. If it takes a lot of energy to heat it up and takes a lot of time to heat it up, it's going to hold on to that energy for much longer. And that's what this statement at the bottom means, right? Lake Ontario is fairly warm all the way into November, even December sometimes, although not this year. When we look at the spring, right, that water is going to stay cold later into the season, right? It doesn't start warming up until July or August, really, when you can kind of go swimming in Lake Ontario and it'll be comfortable. So this imbalance on a daily basis causes these two phenomena called land breeze and sea breeze. So this is the example of a sea breeze, right? We have cool water where we're going to form high pressure, which is going to cause the air to sink. Over the land, which is going to heat up faster, you're going to have warm land, which is going to heat up the air above it and cause the air to rise. You're going to have low pressure. So the land heats up faster than the water. Warm air is going to rise, and then it's going to expand, and then it's going to cool and sink over the water because the water is going to be cooler. This is during the daytime, right, when the sun is heating the land. So we've got high pressure over here, over the cool water, and low pressure over the warm land. Now this is going to flip at night. At night, we're going to get something called a land breeze. So the land is going to cool off faster than the water. So my high pressure area is now going to be over the land. And the warm water is going to be warming the air above it, and that's going to cause lower pressure. That's going to cause the air to rise up. Now, this process switches back and forth depending on the time of day or night, right? At night, we're going to get that land breeze. We're going to get the air moving from the land out over to the ocean or the lake or whatever it is. And the opposite's going to be true during the day. It's going to flip back, going the other direction towards the low pressure on the land. Remember, air is always moving from high pressure to low pressure. So we got our low pressure right here over the water because it's warmer, and our high pressure over the land. So monsoons. Monsoons is a weather pattern that we don't really have here in the northeastern United States. But in parts of Asia, Africa, places closer to the equator, you get these things called monsoons. So in the summer, the air over the continents has low air pressure, and the air over the sea has high air pressure. The pattern is going to reverse in the winter. Reversing winds are called monsoons. So those are those in-between times. So here we have summer monsoon winds. We've got high pressure over the cool ocean, low pressure over the hot land, right? During the summertime, the sun is beating down, it's heating up the land faster, and we're getting low pressure. So the air is going to be going from over the ocean to over the land. It's going to flip in the winter season. That's going to reverse. We now are going to have cooler, high pressure air over the land that's going to go out over the ocean. And you can see we got heavy rainfall here by the coast as it intersects that kind of water heavy land, heavy air that's going to be then cooling when it gets over it. All right, moisture, right? We think about water, we think about liquid water, we think about all of the different phases water can be in at the surface of the earth. Now, there's a whole bunch of information on page 1 of your reference table that's going to show you what's happening here. All right, so when we go from ice to liquid water, we call that process melting. The opposite direction, we're going to be going from liquid water to ice, that is going to be freezing. Evaporation, that's liquid water evaporating into water vapor, which is invisible. We cannot see it. The opposite of that is going to be condensation, when we cool down water vapor and turn it back into liquid. You can see, if you look at these arrows, it tells you what's happening to the temperature. So melting, obviously, we're going to be adding heat to melt. And in cooling, in freezing, we're going to be taking away heat. We're going to be cooling it down to go from liquid to solid. 2 you might not be aware of. Deposition, that's where we go from a vapor all the way to a solid. We skip the liquid phase. And then sublimation, that's when we go from a solid phase all the way to a gas phase. All right, so how much energy is required to change liquid water into water vapor? That's 2,260 joules per gram. So every joule is a measure of energy, and for every gram, we need 2,260 of them to change 1 gram of water from liquid to water vapor. All right, how much energy is required to change snowflake to a raindrop? That's 334, so it's less. All of these figures are in your reference table on the very first page. All right, so relative humidity. This is the comparison of the amount of water vapor the air is holding to the amount of water vapor it can hold. So the higher your relative humidity, I want you to think about it as if the air is mostly full. So warm air can hold more water vapor than cold air. In order to measure this, we use a sling psychrometer, right? We did this in lab, or we're going to do this in lab, and this is something that we spin and we measure the humidity. We also have a hygrometer. That's another way of measuring our relative humidity. So evaporation is a cooling process. This is how sweat works, right? When you're outside working out, you start to sweat, right? That's a way for your body to cool off, because the process of evaporating, the changing that liquid into a gas, is actually pulling energy from you. It requires energy. So the amount of cooling depends on the rate of evaporation. So the greater difference between the dry bulb and wet bulb temperature, the drier the air, so more evaporation is going to take place. If my dry bulb and wet bulb are very close to each other, that means my air is almost nearly full. So that's going to be a very high humidity day, and there's not going to be a whole lot of room for more moisture to enter the air. So evaporation is going to happen a whole lot less. The drier it is, the more evaporation is going to occur. All right, so we're going to be looking at page 12 of our reference table. So we're going to locate the dry bulb reading on the left-hand side of the chart. We're going to subtract the wet bulb reading from the dry bulb reading, and then we're going to locate the difference along the top of the chart and follow our columns down. So I want to show you how to do this on our actual reference table real quick. So here is our chart right here for finding our relative humidity. So the first thing we need to know is our dry bulb temperature. So if I look at the problem that was on the page, it said our dry bulb temperature was 28 degrees Celsius. So I'm going to go over here to dry bulb and I'm going to find 28 degrees Celsius. So it could be any point along this row. for our relative humidity. The next thing I need to do is I need to find my wet bulb temperature, but I'm not going to be using just my wet bulb temperature up here. So if I notice, my wet bulb temperature is going to be 20 degrees. There is no 20 up here. So it's not exactly just our wet bulb temperature that we're using. We need to find our difference between our wet bulb and dry bulb temperatures. So that's a subtraction problem. So I'm going to take 28 minus 20, which was our wet bulb. And I'm going to get my difference as 8. So now I'm going to see right here I've got 8, and I'm going to go down this column and see where these two intersect. So I can see that my relative humidity is going to be 47%. These are all listed as percentages. You can see over here my furthest left-hand column, if my difference is 0, which means my wet bulb and dry bulb are the same number, that is 100%. That means your air is totally full. So let's look at that problem. We've got dry bulb at 28, wet bulb at 20, my difference was 8, and we used the chart to find my relative humidity was 47. This is it. All right. So we're also going to be using our chart that's just below that to find our dew point. And it's the exact same process. So let's take this example where we've got a dry bulb of 4 and a wet bulb of -2. If I find the difference between those two numbers, it's going to be -6. All right, so the relative humidity for this one, we're not doing dew point for this one, sorry, got ahead of myself, is going to be 4. We find our difference is going to be 6. So I see where those intersect, and we get 14. This is our relative humidity again, 14%. All right, now this one, dry bulb and wet bulb, they are the same number. Our difference is going to be 0. Remember what I said about ones that are 0. It's going to be 100%. If our two dry bulb, if those two numbers are equal to each other, our dry bulb is equal to our wet bulb, it's going to be 100% humidity. That means the air is full. So the dew point, this is the temperature at which air cools in order to be saturated. So it's going to be full of water vapor. This is also when condensation starts to occur. Cold air holds on to less water vapor than warm air. Once again, we're going to be using our hygrometer and psychrometer to find our dew point and this chart. So let's practice a couple of these. If my dry bulb is 28 and my wet bulb is 20, once again, we're going to find that my difference is going to be 8 degrees Celsius, right? We're going to be using the same exact process, just a different chart. And it's the chart that's below the relative humidity chart. So let's do this again. 28 for our dry bulb. 8 for our difference. I'm going to see that my dry bulb, my dew point temperature is 16. This is the dew point temperature. That's the temperature that the air would have to cool down to in order to start condensing out water. So we got 16 degrees Celsius there. Let's try this other one. 4 and -2. My difference was 6, and the dew point popped up there. You're going to end up with a dew point temperature of -19 degrees Celsius. All right, last one, -14, -14. If the difference is 0, just like the other one was 100%, this one's always going to be 0 for our, the same number for our dew point, right? It's already at the dew point. This is fully saturated air. How do clouds form? So air is going to be rising and expanding. Now remember, when air rises, it's going to start to cool down as our pressure decreases and it starts to expand. The air is going to then cool to the dew point, and water vapor is going to condense on some sort of condensation nuclei, so dust, pollen, ash particles, something that is in the atmosphere. We can't just condense water out of, thin air. It has to actually condense onto something. All right, so we got this example right here. You can see the air starts here at the bottom. As it rises up, my temperature starts to decrease. It gets closer and closer to the dew point, which is 58, and up here at 6,000 feet, the temperature has now reached the dew point, and we can see that a cloud has formed. Now, how far away that the original temperature is from the dew point is going to determine how high up our clouds are. The further those two things are away from each other, the higher up your clouds are going to form. And in fact, if your air temperature reaches the dew point at the surface, it's going to form a cloud at the surface. That is what we call fog, right? Fog is a cloud that hasn't made it all the way up. It's basically the air starts to rise and immediately hits the dew point and begins to condense into a cloud at the surface. So if you've ever wondered what it's like to be in a cloud, if you've ever been in fog, That's what it's like to be in a cloud. You've been standing in one, you just didn't even know it. So here's a quick time lapse of some clouds forming. You can see how the clouds seem to be growing up, and that's because as the air is rising, it's reaching that dew point and starting to condense. You can see that's how clouds kind of build on each other. They just kind of grow from a spot right here. You can see right here at the base of the clouds, right? There's nothing below that because all of the air below that cloud base is not at the dew point yet. It has to get to that point. It has to rise up to where it reaches that dew point and starts to condense in order for clouds to form. And then as it continues to rise, it continues to cool, and it continues to build more and more clouds. All right, so everybody's favorite, precipitation. So what is precipitation? Precipitation is the form, is anything where water is coming out of the sky, right? Basically whatever form it might happen to be, in liquid water or frozen water in the case of snow, or all those things. It's all the things that we use to describe things coming out of the sky and precipitating out of the atmosphere. So what is the difference between some of these things like sleet, freezing rain, and hail, right? We all know what rain is, right? We all know what snow is, but these other ones that are kind of in between, they can be a little bit more confusing. So let's talk about it. So sleet is going to be when raindrops freeze as they fall. So typically what happens is there's a cold layer way high up in the atmosphere, a warm layer kind of in between, and then another cold layer. So we've got snow starting up here, and as it starts to fall, it melts a little bit, and then it refreezes as it hits this cold layer right below it. Freezing rain. This is when rain freezes when it touches the ground. So it's a very, very small cold layer right at the surface. We've got this large warm layer where the snow that originally starts up here, high up in the atmosphere, melts completely. And then when it hits the surface, it instantly freezes. This can be really damaging. The ice can build up on trees, on power lines, and all sorts of things, and cause a lot of problems, right? Because the trees aren't made, or they don't grow to carry all that weight, so it can cause extreme damage. Back in the 90s, there was a really bad ice storm in Rochester in Greece, and ask your parents about it. I'm sure they'll tell you all about it. Here's some pictures though, right? We've got trees bent over, trees snapped in half. It caused massive power outages, massive destruction. And fortunately, we haven't had a really bad one since. But this happens all over the country, right? These massive ice storms that can be really, really damaging. So hail. A lot of people talk about hail, and they get hail confused with sleet and snow and freezing rain. But hail is a very specific phenomenon, right? It's these large chunks of ice that come out of the sky. And hail usually actually happens in the warmer months. All right, so here's a quick video of some hail. You can see these are large, fairly like golf ball size diameter chunks of hail that are coming out of the sky. And the way hail happens is when we have a very low pressure system that has very strong updrafts. Look at that, they're bigger than the quarter. Very strong updrafts. We've got water that is precipitating out and begins to fall. Now, the strong updraft, the strong amount of air that's going up, rising, pushes that water back up into the cloud, which causes it to freeze. And then it begins to descend again when it gets too heavy. And then it melts a little bit and gets pushed back up into the cloud. And this freezing over and over and over and over again grows our hail. So the more it does that, the larger your hail is going to be. Now, we often associate hail with very strong thunderstorms, right? Because those are very low pressure areas. And it's been pushing that rain back up into the atmosphere and forming these larger hail pellets. All right, how do we measure precipitation? Well, we can use a rain gauge to measure rain and a ruler for snowfall. We usually express snow in how many feet of snow fell. And rain, we usually talk about how many inches of rain has fallen. We use these rain gauges to capture that rain to do that. All right, I want to talk about a few atmospheric relationships. So, air temperature and the capacity to hold water. So as temperature increases, capacity is going to decrease, right? So the amount of water it can hold is going to increase. That's going to be a direct relationship. As one thing increases, the other thing increases. So as my temperature increases, so does its ability to hold on to water. Temperature and density, right? We've talked about this quite a bit. So as my temperature increases or decreases, my density is going to decrease as well. Oh, excuse me. Let's go back. All right, let's take a look at temperature and density. So as temperature increases, density is going to decrease. As we heat things up, the density is going to decrease. Now, this is true of liquids and gases and all the things we're going to be talking about later on in the year. Temperature and air pressure. So as temperature increases, my air pressure is going to decrease. So this is another indirect relationship, just like the last one. As one variable goes down, the other one goes up. So as my air pressure decreases, my temperature is going to increase, or vice versa. As my temperature increases, my air pressure is going to decrease. All right, relative humidity and air pressure. So as relative humidity increases, pressure is going to decrease. Why is that? Water vapor is a lightweight gas, so that is going to cause my pressure to lower. So the more water you have in your atmosphere, the lower the pressure is going to be, because there's more lightweight gas versus our heavier gases like oxygen and nitrogen. So the difference between temperature and dew point versus the chance of rain, right? The closer the temperature is to the dew point, the greater the chance of rain, as the air is more humid. So let's take a look at this. Chances of rain, that's going to decrease as the difference between temperature and dew point starts to increase. All right, air pressure and the chance of rain. So as air pressure increases, the chance of rain decreases. Remember, think about it. If I have high pressure air, that air is going to be sinking. It's not going to be forming clouds. It's not going to be getting cooler. It's not going to be reaching the dew point, so it's not going to precipitate, right? If I have low pressure air, that's going to be air that has lots of water vapor in it. It's going to be rising up. It's going to be cooling down. It's going to be reaching that dew point, and it's going to be precipitating. So altitude and pressure, last one. As altitude increases, air pressure decreases. So as we go up, my air pressure is going to decrease. Now this is what causes the cooling of that air as it rises, right? As it rises, it's going to expand, it's going to cool down. That does it for our weather variables. The next video is going to be all about station models and how do we show those weather variables on a map.